We are now going to enter the world of natural convection. So in forced convection, which is the only convection we've really looked at so far, we've got fluid motion, but the fluid motion itself is caused by applied pressure gradients. And when I say applied pressure gradients, I mean we're physically forcing the fluid to move. And we do that via pumps, fans, blowers, and so forth. In natural convection, that is not the case. Natural convection is also called free convection, and the fluid motion is caused by buoyancy forces. So we're going to spend a significant amount of time right here in the beginning reviewing the nature of buoyancy and figuring out how we can quantify buoyancy forces in fluid flow. That's why we have our friend up here. Here's his device to help him with buoyancy. As a review of buoyancy, let's consider the case of a rubber ducky floating beneath the surface of the water in a bathtub. Here's our rubber ducky friend. So there are two forces acting on our rubber ducky. One of them is the weight of the rubber ducky itself. So that would be the mass times gravitational acceleration, or if we write the mass as the density of duck times volume of duck, we get rho vg, where rho and v are that of the duck. The force that the water surrounding the duck exerts on the duck is the buoyancy force. So in your fluids class, you learned that that was the weight of the displaced fluid. So we write that as rho of the water times volume of the duck times gravitational acceleration. If we look at the net upward force, that is, taking this buoyancy force, which is acting up, and subtract from it the weight of the duck, the net upward force acting on our rubber duck friend would be FB minus W. When we substitute these expressions in there, since it's the same volume and G in both of those, we get rho water minus rho the duck times V duck G. The important takeaway from this little equation is the following. The net force upwards depends on the difference in density between the rubber ducky and the surrounding fluid. So it's the difference in density that provides the net upward force. We see it here explicitly, rho water minus rho duck, V duck times G. So there's a very quick review of the idea of buoyancy and the net force on something acting in the upward direction away from gravity being the buoyancy force minus the weight of our object. Let us now consider, rather than a rubber ducky sitting underneath the surface of the water in a bathtub, let's say instead that I've got a fluid particle. And it's not sitting inside a bathtub, but rather it is locally at a warm temperature. It's hot, and it's sitting in a fluid that's not. Right? So this is not rubber duck. This is a fluid particle that locally is at a higher temperature than the surrounding fluid at out here. So we can repurpose that equation, and in place of rho of the surrounding fluid, I just have rho of fluid in general, and in place of rho of rubber ducky, I have rho of the hot fluid particle and V particle. So when you look at this equation for a locally hot fluid surrounding by a cooler fluid, you see that once again, the difference in density gives you a potential net upward force. What do you know about the density of fluids that are warmer compared to densities of fluids that are colder? For instance, what if you were thinking about an ideal gas? Write the ideal gas equation in terms of density, solve it for density, you get this. Rho is equal to P over the quantity RT. Temperature goes up right here. If T goes up, what happens to rho? Rho goes down. Right? So you've all heard hot air rises. Now you see why, because large temperatures, low densities, that means this density difference between your local air and the surrounding air is such that you get a net upward force. So the takeaway from this is the following. We see that if you've got a temperature difference, that can cause a density difference. And density differences in turn can cause buoyancy forces. And those can, okay, they don't necessarily have to, right? But they can cause fluid motion. And if you've got a moving fluid, that means you've got convection. So this is what causes natural convection, these difference in temperatures eventually leading to fluid motion without your having to physically force the fluid to move with a fan, pump, blower, etc. So now let's take a closer look at this idea of a density change. So we're going to define a property of our fluid, beta. So beta is defined as minus 1 over density, partial derivative of density with respect to temperature, where you're taking P and holding it constant. All right. This property is called the volume expansion coefficient. Sometimes it's called the volume expansivity. When you look at this and you don't see volume in there, you're wondering why it's called that. So there's another way to write this. It's completely equivalent, exactly the same property, which is 1 over volume, d volume dt, holding pressure constant. And there's not a negative sign here, right? So when you look at this equation, you see, oh yeah, if something has a big old change in volume when you change the temperature, it's got a big value, the volume expansion coefficient. What if it doesn't change at all when you change temperature? What kind of fluid do you have? That's going to be one of the questions I ask for you to tell me next time, all right? We're going to stick with the form of beta that's got density in it because density is what shows up in our equations. So this might be more intuitive to you, but this is the form of the equation we're going to use. There is a very famous and very useful approximation to beta that we're going to use pretty much exclusively in natural convection, and it's the following. Let us assume that beta is constant over the delta T range of interest. Okay, so densities aren't going to be constant, but we're going to are going to assume that beta itself is constant. If that's true, then beta can be rewritten as approximately 1 over some standard density times delta rho over delta T rather than d rho dt. All right, and if we solve this for delta rho, we get that delta rho is minus rho beta delta T. Here's the utility of this equation right here. You got some density. You change the temperature of your fluid locally, multiply it by beta. Now you've got your decrease in density of that fluid. So this is one form of what is called the Boussinesq approximation, named after a famous 19th and 20th century mathematician and scientist from France called, you guessed it, Joseph Valentin Boussinesq. And whenever I hear Boussinesq, I always think of this region in France called Beaujolais. Now, Boussinesq himself was actually down here. That's where he was from, but he was probably pretty close to Beaujolais, and he certainly knew Beaujolais because Beaujolais is a beautiful, picturesque place where they've got lots and lots and lots of grapevines, and they make a wonderful, tasty wine that's named after the region called Beaujolais. It's one of the few red wines that is actually much better when you drink it young. It's not one of the red wines that you like to have age for years and years and years and it becomes better. So it's one of those few red wines that actually is good when it is younger. Speaking of red wine, I've actually done a very, very hardcore scientific survey that shows how exam averages and their standard deviations change as a function of the beverage that your professor is drinking as he or she is grading. We start with red wine. Averages tend to be high, standard deviations low. If your instructor is drinking beer, the average tends to be high, but the standard deviation also high. In terms of scotch, averages are low. Standard deviations, high. And if your instructor is drinking vodka, you're going to have a low average, probably a low standard deviation too. In any case, let's get back to the problem at hand. The net force up on our fluid particle, remember, is the difference between the density of the fluid and the density of the fluid that's locally hot times the volume of the particle times g. We've already seen that. Let us now replace that with our delta rho approximation using the Boussinesq approximation. So rewritten in terms of beta, we get minus rho beta delta T g v of the particle. Don't like that negative sign there, so I'm going to incorporate the negative sign in the change in temperature, and I get this instead. Rho beta T minus T infinity g times volume. Now, in the case that your fluid temperature locally is warmer than the surrounding temperature T infinity, when you look at this expression, you get that you have a net force that is positive when it is going up. In other words, if you've got a locally hot fluid, the net upward force can cause the motion of the fluid to go up. On the other hand, what if this isn't a hot fluid particle, but a locally cooler fluid? It's got T less than T surroundings. In that case, this tells us that the net force in the upward direction is actually negative. In other words, there's a net force going down. This can cause your fluid to move too, but it could move down instead. As a little exercise to consider how these local temperatures can affect fluid motion one direction or another, we've got this following scenario, right? So I'm not going to fill in the notes in this little half a page. You're going to actually fill this in on yourself by thinking about this and bring it to me at the beginning of class next time. So we've got two plates in this exercise, and they're separated by a fluid that, at least initially, is just standing still. It's not moving at all, right? And then we suddenly are going to heat one of the plates. In case A, we heat the top plate, and in case B, we heat the bottom plate, right? In both cases, I should make clear here, gravity's arrow is facing this way. Case A, T1 is greater than T2. Case B, T2 is greater than T1. So I'm asking you to tell me what happens in these two different cases. Does the same thing happen or not happen? Specifically, I'd like you to try to do the following. I would like you to tell me what the direction of the heat transfer is in the fluid and draw an arrow on the diagram that shows that. The next thing I want you to do is tell me what's happening with fluid motion. Is it up, down, left, right? Not at all? I'd like you to next tell me, based on the previous answer, what the mode of heat transfer is in case A and case B. And last, I'd like you to tell me for case A and case B what the Nusselt number is. Is it less than 1? Is it equal to 1? Or is it greater than 1? So this shouldn't take you more than a couple of minutes, but do have it filled out and ready to present the rest of class when you come at the beginning of next time. So if buoyancy is moving our fluid, there might be something that's trying to slow it down, the fluid friction. And that thing, of course, is viscosity, viscosity being essentially fluid friction. We would like to define a dimensionless number that measures the relative importance of those two ideas. So it's going to be a capital G, lowercase r, GR, and it's buoyancy forces divided by viscous forces. We are going to write for our buoyancy forces the expression that we derived for the local force on a little fluid particle with the Boussinesq approximation. Rho g beta T minus T infinity times volume. And for the viscous forces, we're going to write mu. The more viscous the fluid, the more viscous resistance there is to that flow. This would be an awesome dimensionless number if it were dimensionless. It's not. Okay, so I'm going to cheat. I'm going to square viscosity and divide by rho. The resulting number is now, in fact, dimensionless. Okay, this is not the rigorous way to derive this number, but intuitively it makes perfect sense. And if you believe that this is dimensionless, it should do the same job. So we're going to do that algebra, and I've made a couple of changes. One, this temperature right here, well, let's not use the temperature at every point in the flow field for the local fluid particles. Let's just use a nice reference temperature T surface. Likewise, volume of a particle, well, that's hard to measure. So let's use L, which is some characteristic length in our flow, and cube it. And now we have the dimensions of volume. This might be a length of a plate. It might be a gap distance between two plates, something like that. We're almost in our final form. We've got mu, we've got rho. Do you remember what mu over rho is? It's nu. That's right, the kinematic viscosity. So here's the final form of our dimensionless number. G beta delta T L cubed over nu squared. This is called the Grashof number. That's why we give it the symbol GR. It basically plays the role of Reynolds number in buoyancy-driven flows. Very similar. Why do you think it's called the Grashof number? It's named after this fellow. He was a German engineer of the 19th century. He's the first person to come up with it. Clever guy. We call it the Grashof number. Whenever I think of the Grashof number, I think about how I became very good at natural convection, and that was because I had a very good teacher, a very good master that told me to Grashof, Grashon, Grashof, Grashon, Grashof, over and over again, and I got really good at those calculations. Now it's your time to try. So give it a shot, folks. Oh, you guys are the cutest class I've ever had. So that's the Grashof number. So as I alluded to earlier, a high Grashof number and a low Grashof number kind of play the role of high Reynolds number and low Reynolds number in buoyancy-driven flow, which means that high Grashof numbers tend to be turbulent flows, where low Grashof numbers tend to be laminar flows. This is definitely going to play a major role in what calculation or what correlation you use to find heat transfer coefficient in natural convection. Now, there's another dimensionless number that's very important as well. In fact, you are more likely, much more likely to see this in the actual correlations, and that is RA, where we take the Grashof number and multiply it by the Prandtl number. Okay, this is called the Rayleigh number. Remember, in forced convection, you have Reynolds number raised to some power and Prandtl number raised to some other power in all your correlations. In most natural convection scenarios, the Grashof and the Prandtl number are both raised to exactly the same power. So why not combine them for a new dimensionless number and use that instead? That's what the Rayleigh number is. Hey, can you guess who the Rayleigh number was named after? It was an English scientist. He was really important. What do you think his name was? John William Strutt. You're like, what? Well, why is it not the Strutt number? I'm confused. Well, he was also known as Lord Rayleigh. He was the Baron Rayleigh. So we use Rayleigh and not Strutt. Okay, so a few review questions for you. First and foremost, don't forget to fill in that half a page of notes about that exercise with the two plates, one hot, one cold, in different orientations relative to each other. Next, what is the volume expansion coefficient if you have an incompressible fluid? What's its value? Next, what is a typical set of units for volume expansion coefficient? Don't just look it up. You can look it up to verify it, but look at the expression for beta and see if you can come up with, oh, here's a typical set of units. Next, can there be any natural convection if you have an incompressible fluid? Why or why not? Can you have any natural convection on the International Space Station? I'm assuming, by the way, the International Space Station is still up in space, just to make that clear. What is the interpretation of the Grashof number? What is its job? And last, what would you recommend that I enjoy drinking as I grade your next exam? Red wine, beer, scotch, or vodka?